morning, everyone. It's really nice to be here in Denver, and I see we start at exactly 11:55, so I can still say good morning. So today I will talk about an experiment that me and my team have performed around Zephyr, IREE, and AI, obviously. This required quite some tools and integrations, but I will speak about that. I'm from IMEC, which is a company in Belgium. We are working in compute systems architecture, and I will have more slides about that as well. As you might have guessed, looking at my family name, I'm from Soviet Union. So when I was a child, I was looking at pictures like this, posters from movies, reading books, all about science fiction, you know, about robots, about tablets. Over there in the middle, you see some tablets as well from 1960s. I was really motivated, of course, yeah, to go into science, study computer science, and work on building a good future for everyone. And back in, so if we a little bit scroll forward to 2015, that's when the Tomorrowland was released. And this reminded me a lot of these old Soviet movies and books. And also, as a coincidence, also in 2015, I believe Wind River has open sourced Zephyr, which was originally acquired from a Belgian company. This, I think, brings together, let's say, a little bit from my background and what I'm going to talk about. So my question actually that I would like to address in this talk is what will be the compute system that will power this future Tomorrowland? It's actually not one, but it's many questions. And at IMEC, and you see here an overview of our site in Leuven in Belgium, we are trying to address some of these questions. So the first one is, yeah, will this compute system be using open architecture? We believe so. It will be using RISC-V instruction set architecture. It will be built using Linux, Zephyr, and open systems, OpenXYZ. There are many examples of them. And then the next question is, who will actually design this? I think, obviously, it's not one company that will design it, not IMEC, not Microsoft, not Meta. It will be a collaborative effort. And implementation is always very difficult, as everybody knows. Design is difficult, and implementation is even orders of magnitude more difficult, especially given the compute requirements and compute needs of tomorrow. So it has to be AI, right? But then the question is, who will fund it? It's my belief that the next generation megacities will actually fund this, because megacities is the organizational principle that our civilization has produced that traditionally funds all the new developments. The actual building of these chips, this has to be built by fabs, right? And it's actually a very important topic right now that we are addressing at IMEC, green fabs. How do we build chips using sustainable technologies? And the last question is for you, actually. So will it be open source? Of course it will be, right? That's why we are here. So a little bit about IMEC. IMEC International is not really a company. It's more a research institute, but it's also funded by partners. It serves as the glue between the design houses and fabs. So here you see some examples of fabs that we are partnering with, TSMC, a new one from Japan, Rapidus, and some examples of the design houses, Intel, Samsung, Micron, Qualcomm, all the important players in many different fields. We are present not only in Europe, our headquarters is in Belgium, but we are also having research departments in Netherlands, UK, Germany, Italy, Spain. Also in US, by the way. And we are looking for further expansion. IMEC is 41 years old right now, and here I would like to a little bit explain what my group is doing there. We are actually on the 8th floor of the tower building, and the tower is directly connected to a fab. It's a research fab, not actually producing chips, but we are trying to see how we can scale the technology, how we can get benefits from the technological innovations. So what we are doing is that we are getting our performance requirements, we are defining our architecture, we are getting our reference designs right, and we send them to the fab for testing. What we get from the fab is obviously the area, the power, and the cost metrics that are, let's say, tuned for the future technologies. My group is actually operating within this iceberg. You could see it as an iceberg, a little bit above the water, so we are in the system and SoC architectures, while below us there is a lot. Actually, most people at IMEC are working on technology platforms and core semiconductor technologies. And we do this for many different domains: health, industry, entertainment, education, energy. All right, so we have this vision of AI-enabled mega cities. How do we actually realize that? Because we have to build a lot of stuff. We have to build devices, we have to build networks. It has to be sustainable. So in this experiment that I'm talking about, we have taken Zephyr as our base because it is very flexible, it's very configurable, and it allows us to actually build all these devices. We believe so in the future. The next step is, of course, AI. How do we enable AI on Zephyr? How do we bring these models that are being trained by big companies, foundational models and others? How do we port it on this Zephyr platform? There we have selected IREE, which is an embedded execution environment for machine learning. So what would be the platform that runs IREE and Zephyr? We believe it will be also open instruction set architecture, RISC-V. What we have done there is primarily to make sure that IREE and Zephyr work actually in 64-bit version of RISC-V architecture with vectors too. And we have done some, let's say, cross-stack, full-stack integration of these technologies with some interesting modifications to the Zephyr flow. And last but not least, we believe that all these steps, all these components need to be integrated in a repeatable, reproducible way. And that's why we have also added GUIX, which is a functional package manager and software distribution mechanism to this experiment. So a little bit about Zephyr. Of course, I probably don't have to introduce Zephyr to this community, but we have actually started looking at, or working with Zephyr some years ago for a joint project with Sequans, which is a company from France, from Paris, who are building the next generation 5G, 6G solutions. So what we have done in that project, we have taken FreeBSD networking stack and integrated it with Zephyr kernel, also System C kernel, but that's not the topic of today. For the purpose of emulation of realistic use cases for TCP/IP congestion control. So essentially, we wanted to reuse existing TCP/IP applications that we can just take from open source and run them inside that emulated system. And we had really good results from that project. First of all, we managed to integrate FreeBSD networking stack, and it was also very useful for the customer. I already mentioned Zephyr. It has great community. It's a small minimal kernel, supports real time. I see it really as a library OS where it provides runtime functions that are needed for applications, and only those functions, no unnecessary bloat added to the final binaries. And it is also very customizable, so you can add new BSPs. And also, one of the major reasons why it was possible to actually port the IREE on Zephyr was the presence of the POSIX layer in the Zephyr. So what did we actually do? We created our own BSP for our simulated and emulated systems. We have both Gem5, which is a simulator, and FPGA, which we used as an emulator. And I will show it later. We actually tried to calibrate them so that the performance metrics from Gem5 actually correspond to the performance of the FPGA. But to get there, to actually run those benchmarks, we had to create a new BSP for Zephyr, and that included a serial driver. As you might know, almost every platform prefers their own flavor of the serial protocol, the protocol between the serial hardware and the core. So we had to adapt that one. We added SoC support for this Gem5 FPGA combination, specifically including only features which I use there, and of course board support. So in Zephyr, you need to have all this free in order to get useful binaries out. So besides that, we have also changed a little bit the build procedure because, especially for Gem5 simulator, the system didn't really expose the storage subsystem. So we had to actually include the storage together with the image. And for this, some modifications were required in Zephyr. So we essentially reuse the DOS file system, which is supported in Zephyr, but we actually had to mount it not from external storage device, but from the image itself. So when Gem5 boots, it actually loads the whole image, so it is in memory. After that, it can be mounted. So what did we put in that file system? I will show it also later as well. For IREE run module program, which dynamically is able to load new modules into the runtime and run them. We had to actually add some arguments so that it knows basically which parameters are needed and what needs to be initialized. This same file system also will contain the flat buffer image for the IREE module binary bundle. And yeah, if you're familiar with IREE, you will know that it contains the virtual machine code for the control side of it, and also actual binaries for the accelerator. So some models obviously also require inputs. They require, especially for tests, you need to basically include the images for MNIST, for example, or some text that needs to be cross-checked with the output from the model. So we also add that to the image. And then we just DD it. So there's this Unix command DD, which essentially can just copy some data into the image. That was all fine, but of course we wanted to make everything in a repeatable, reproducible way. So actually, we got some help already out there because there was the project on GitHub which already created GUIX packages for Zephyr, including the SDK, including the Zephyr checkout and all the scripts. So the only thing we needed to do is to actually upgrade that one. So what is IREE? Just a quick summary. It is both a compiler built on LLVM and a runtime for running results compiled by that compiler. The compilation results in a module. So essentially you give your TensorFlow Lite model. You can download the modules, the TensorFlow Lite models from many sources. So I think one of them was the Hugging Face for GPT-2, and there were other sources as well. And then you can get from the compilation of that, you basically get this VMFB file here. And then that file can be run. So normally, IREE runs on Linux, so this VMFB can be given to the IREE run module, compiled for Linux, and then it runs it, utilizing all the available accelerators that you select. In our case, of course, it needs to run on Zephyr. But the flow is the same. We didn't change that. One thing to note about IREE, it's a pretty complicated project, which relies on MLIR, it relies on LLVM, and that comes with a lot of other dependencies. So it's difficult to build, difficult to package, difficult to validate, difficult to deploy. Of course, unless you just download the binary, but I think everybody wants to build from source, right? So what did we do there? To simplify that, to improve it, we actually had to add some, or improve some support of IREE and HAL, the hardware abstraction layer, to support 64-bit. We added some additional testing, debugging. We added also a GUIX package for IREE. Here you can see, well, you cannot really see, but it gives you an impression of a dependency graph. So IREE package is here, and these are all the packages that it depends on. It's pretty impressive. And next to that, we also added an automated suite to actually benchmark the running of these compiled IREE modules on different platforms, including GPUs and other RISC-V platforms. How did we do it? We had to actually bootstrap it on Zephyr. So, you know, when you take a big, complicated software project, it will not work out of the box, especially on a platform that is not built to support originally. So we had to actually start with really simple hello world kind of examples. So you actually see here also some IREE code, which I think it was intended to show how well engineered IREE is. So it's very nice. Follows nice software engineering practices, does all the error handling, all in a perfect way. But of course, it all needed to be debugged. It needed to be verified to work. So we actually created initially a very simple kind of hello world application, which does only a very simple MLIR ops, doing pointwise vector multiplication. And by running that, we could verify it also on this simulated emulated platform. It works actually identical in both platforms. And of course, after having solved all these issues, so our next step after the hello world for IREE, we had to do the hello world of AI, which is of course the MNIST, the one that detects digits, handwritten digits. So we created a separate Zephyr application which did MNIST on all the digits from this file, included in that file system that we bundled together with our L file. And of course, we verify results that all the digits are detected correctly. After that, the next step is running MobileNet, which is an image classification model. It's a very large one, so running it on the simulator, on GM5 simulator, it took actually quite a significant runtime. And last but not least, we managed to run many other models. You see here some snapshots. I'm not sure you can actually see, but there is POSNet, Magenta, EfficientNet, ResNet, DenseNet, and so on. Last but not least, we managed to even run GPT-2 on it. It took, I think, for the FPGA, it took about 40 minutes to run one character inference, basically, and for Gen5 it takes about 4 hours. So, so we have done some work on Zephyr, as I have shown. We have done some work on IREE to improve it, to make it more, let's say, portable. So where do we actually run these two things on? And I have already mentioned that we did it on RISC-V. So why RISC-V? RISC-V is obviously yeah, quite a hot topic nowadays, but the real reason behind it, why is it interesting, is that it's modular. The modularity of RISC-V is manifested by these modules that you see here, the different modules, different letters here around the circle, and they represent extensions to the instruction set architecture that you can actually define yourself as well. But the other project that IMEC did in this domain was to actually improve the modularization of instruction set simulators that arise out of the golden model. Golden model is the reference model for instruction set that RISC-V specifies, and we managed to increase performance of the instruction set simulator at some expense of the code size. But how do we actually link this work to the academic microarchitecture simulators such as GEM5? GEM5 is a pretty well known. I think many companies use it, and also universities build their work on it. And primary reason for that is that it implements many different models of the microarchitecture. So the CPU, RISC-V CPU in our case, it has many components, small and large, and all these components need to be modeled. The IPs need to be verified, and dependent on the fidelity level of the CPU model that you are interested in, you will have more or less of these IP blocks actually simulated in a simulation. So this results in a quite flexible way of addressing this performance modeling. But on the other hand, it introduces some difficulties as well. So similar to IREE, it also goes quite far in trying to decouple, for example, the front end of a core from the back end of the core. And as a result, it also is difficult to build, difficult to package, difficult to calibrate, difficult to deploy. And very, very often when you try to use GEM5, you realize that there are so many layers in the simulation that, for example, you can have some C++, let's say, main function, which is calling to a Python interpreter, which is interpreting some model configuration parameters, which is then calling to, again, some C++ components, which are then depending on whether or not you integrate GEM5. But other simulators might also involve some extra layer of Python there, so it's basically like a sandwich architecture. To highlight a little bit on validation of this platform, let me explain this. So we have some microarchitecture running in FPGA, and some microarchitecture simulated in the GEM5 minor CPU model. So this includes quite detailed models of both the core and the cache subsystem. And the calibration of these two against each other basically involves tuning the parameters in GEM5, tuning parameters on FPGA to try to converge to a common performance model. So what did it result in? Using micro benchmarks that we used, let's say, to bootstrap this calibration process, which essentially also are available on GitHub. Really simple loops, simple control flow. We managed to basically calibrate it pretty well. So within, in the end, within 14% of mean absolute percentage error for IREE models. That all was made possible by also leveraging the detailed simulator for the memory of the system, and there we reused the Remulator 2 simulator. So here on this graphs you see some of the IREE models. So MNIST is here. It's one of the simplest models. And the more complicated ones, such as Magenta, PostNet, they take much larger errors for calibration. All right, so how do we integrate all of this work? Because as you might imagine, this took us quite a while to get it all running. These are complicated, let's say, stacks, each of them. Okay, Zephyr is not that complicated, thankfully, but IREE is, and Gem5 is also complicated, and of course, running things on FPGA is also quite involved. So we essentially first wanted to get the spec benchmarks, spec-int in this case, working. We managed to integrate it with them with Zephyr as well. Well, at least some of them, I would say, not full spec benchmark set. And I think you can find it actually on our GitHub. Next step after that was the MLIR and IREE workloads, which were, as I said earlier, imported from TensorFlow Lite. But I have to say that ONNX import works as well. And these workloads, they have to be, of course, running on both the CPU and the accelerator. So we packaged all that, and then we focused on the control side of it, on this core, which actually runs the VM code produced by IREE to transfer data to the accelerator, transfer results out from the accelerator, and trigger the computation. RISC-V, yeah. So by the way, the FPGA that we used is AMD, so Xilinx VC128, which was actually also quite involved to actually port some code to it, because for the core we used ChipYard, which is a project from Berkeley, implementing many different systems, and one of them is a Rocket Core, which is a RISC-V 64-bit CPU. So combining all that and looking at the benefits, let's say, of doing this, we basically see that we can take deep learning models, we can generate a framework-independent representation from them, we can generate, let's say, hardware-optimized representation, accelerating some functions from the MLIR stack, such as, for example, the gems, matrix multiplies, matrix vector multiplies. We can integrate it all using the lightweight runtime, the Zephyr, with the POSIX support of Zephyr. By the way, IREE requires actually POSIX at many levels. They use the threading subset. They use also memory management as well. So we actually had to debug quite some memory management bugs there as well. And in the end, we can run them. The same binary runs on both Gem5 and FPGA. And it's relatively slow, of course, on Gem5, but on FPGA, we get decent results. So these are our results. Here you see some speed up for the IREE models that we have run. And here you see a distribution of the instructions that Gem5 reports. So for example, we see memory instructions, we see floating point instructions, we see vector instructions. So to highlight a little bit on why we use GUIX, let me explain it a little bit. By the way, how many people know or have heard about GUIX? Okay, just one. So let me explain. So as I said earlier, GUIX is a package manager and a Linux distribution. as well. So what it brings on top of existing solutions is full repeatability, and it is essentially a functional package manager. So any kind of environment variable or any kind of configuration setting that has impact on the build, it leads to build producing different binaries, needs to be captured. So when you get a binary and you rebuild it from the same sources, same package on another system, you should get, you will get always the same binary. So to achieve that, how they do it in GUIX, they have a package description. It's written in Scheme. The package description includes all the references. So there are different kinds of dependencies that you can imagine. There are dependencies which are needed to actually build the outputs. So if your build generates some binary, and for that one you need some library, well, it has to be in the list of inputs. On the other hand, you can have let's say, inputs which are used by the binary after it was built, or it is only used, such as, for example, in the case of static libraries, when you are building and not later. That would be included in native inputs. And then you have additional kind of input, additional kind of dependency in GUIX, which is called propagated inputs. That would be the dependency which you will need not only after you have built your output and actually use it, but also when the output, if the output itself is a compiler and it will generate another binary, so the next stage after this, it would also need this input. So it's essentially input that needs to be propagated through the whole dependency chain. And I was quoting a little bit from Phil Wadler, who came up with the story of have you used it in anger? And basically what he meant with that story is that we come up with solutions, and the solutions need to actually work out there in the wild. So even if you have, let's say, a bike, a very nice looking bike, it still needs to be a bike that can bring you across a desert or across a forest. So we believe that GUIX is a solution there, because it seems to provide all the necessary ingredients for all this complicated building of modern-day software in a very different kind of environment. So we can, for example, build all these packages that I have been describing on HPC clusters, on inside Docker containers. We can build it in WSL on VM on Windows. We can build it on all Linux distros and so on. And it always results in the exact same binary. That's an incredibly powerful solution. So maybe, looking at time, I will just briefly mention that describing GUIX packages is not very difficult. It's essentially like Lisp or Scheme, where you essentially define all these things that I talked about. So native inputs. You, of course, also, last but not least, have to specify which license it has, and all the other metadata, such as descriptions. And of course, the source, where are the sources for this package? And as a result, after you GUIX built this package for Gem5, you get again a very complicated, let's say, set of dependencies satisfied with all the dots here representing package and package versions. All right, so how do we use this? Once we have described all our components, so Zephyr was described, Gem5 was described, and IREE was described. We have all the descriptions. So how can we leverage this? So essentially, we can leverage for building, let's say, new releases. So here we say, okay, now we have a package for Gem5. Let us now build a new version of it. Suppose we have changed like tiny bit here and there. So this command here will essentially import all the development dependencies of Gem5 into the environment, and then add the GCC toolchain to it of this particular version, and then we run the Gem5 specific build commands. That's a very useful way. So you don't actually have to anymore tell anybody how to actually build it, which steps to follow in the manual. You can just give this command, and everything will be happening automatically after that. Also, we can run software with it. We can run Gem5 again using all these environments described earlier, and actually get reproducible results from our reproducible builds. That's the main message here. So yeah, to summarize, what was our contribution to this full stack hardware-software system integration? We have looked at Zephyr. We have taken Zephyr. We have added board support packages. We ported IREE on it, and I believe IREE should become the default AI subsystem for Zephyr. So yeah, I think I should probably mention that all our work is open source, so you can find it on this at this URL. And I would like you to join us in this journey, because yeah, what I've shown so far is actually only the inference side of AI. Our future work includes actually bringing distributed training to the edge, also using Zephyr, IREE, and let's do it together. Thank you.